everyone. Now I would like to talk about the assignments 2 for the course SSCP 2613 Session 2 Mathematical Physics, which is mathematical model of a coilover shock ensemble. In my group, which is group 3, there is 3 group members, which are Asiki, Danny, and Kasnina.
Good day everyone, my name is Nur Ashiki binti Saiful and I will be presenting part 1 of our assignment 2. A coilover shock absorber is a suspension device widely used in automobile. It consists of 2 main components, namely the coil spring and the damper. The damper is positioned at the center of the spring. When a vehicle passes over a bump, the coilover oscillates. According to the assignment brief, this oscillating motion can be represented using a second order ODE. In this model, the spring is assumed to be at equilibrium length and the weight of the vehicle is ignored. The coil springs support the vehicle and absorb impacts from an even root surface. When compressed, it produces a restoring force that helps return to the suspension to its equilibrium position. The damper works together with the spring by reducing excessive vibration. It provides resistance during motion, allowing the oscillation to gradually decrease. Together, these 2 components improve ride comfort, vehicle stability, and handling. The motion of the coilover can be described using Newton's second law. 2 forces act on the system, the restoring force produced by the spring and the resisting force produced by the damper. Combining these forces give the governing equation, which is mx double prime plus cs prime plus kx equals 0. Here, m represents the mass, c is the damping coefficient, k is the spring constant, and x is the displacement from the equilibrium position. According to lecture 13, we solve the second order differential equation by assuming the solution has the form x equals e to the power of rt. After differentiating and substituting into the governing equation, we obtain the characteristic equation mr squared plus cr plus k equals 0. The roots of this equation determine the behavior of the suspension system. The characteristic equation determines the damping condition of the system. When there is no damping, the system oscillates continuously. In the underdamped case, the oscillation gradually decreases over time. For the critically damped case, the system returns to equilibrium in the shortest possible time without oscillating. In the overdamped case, the system also returns without oscillation but at a slower rate.
I'm Danny. Now I will present the simulation results. For these simulations, we use a mass of 2.537 kg, a spring constant of 18.624 Newton per meter, an initial displacement of 0.100 meter, and an initial velocity of 0 meter per second. We only change the damping coefficients C to compare the 4 damping cases. The purple graph is the undamped case where C equal to 0. It oscillates forever because there is no damping. The blue graph is the underdamped case where C equal to 15.200. It still oscillates, but the amplitude gradually decreases until it reaches equilibrium. The green graph is the critically damped case where C equal to 28.603. It returns to equilibrium the fastest without oscillating. Finally, the orange graph is the overdamped case where C equal to 14.850. It also returns without oscillations but more slowly than the critically damped case. These graphs clearly show how damping coefficients affect the motion of the systems. Now I will pass the presentations to the next speaker, Kasina.
Now that we have looked at the data and individual characteristics of each system, I want to compare all 4 graphs to see how different damping conditions completely alter a system behavior. For the first case is undamped case form. As you can see the purple color graph, this is the system that oscillates forever because there is zero resistance or friction, the amplitude never decays and it continues to cycle indefinitely. Second is for the underdamped graph. As you can see the blue color graph, the system oscillates but gradually stops. The resistance is light, so while the object swings back and forth past the equilibrium point, each wave gets smaller and smaller until the energy is entirely dissipated. Next is the critically damped graph, which is the green color graph. This is a unique sweet spot. It returns to equilibrium the fastest without a single oscillation. It crosses back to its baseline in the minimum amount of the possible without overshooting. And lastly is the overdamped graph, which is the orange color graph. This system also does not oscillate, but because of the damping force is so massive, it returns to equilibrium very slowly, and it feels sluggish and heavy, taking a long time to crawl back to rest. So, which condition is best for a rear car suspension? The answer is critically damped condition is the most suitable. This is because an undamped or underdamped car would bounce endlessly, causing motion sickness and poor handling. An overdamped car would react too slow, making the ride incredibly harsh over repeated bumps. In conclusion, we can conclude that critical damping provides the perfect balance. It absorbs the shock and returns the vehicle to a stable level position as quickly as possible without any bouncing to ensure both safety and smooth ride.